For all those who appreciate the work that we're doing here on Standing for Truth, please hit that subscribe button because we are just getting started.
My name is Maarten and I will tell you something about heat during the flood. Is heat a problem or an answer? There are many flood models available, but they all have one problem in common. They have too much heat involved. And take a look at this statement. A sudden exposure of the mantle to 70% of the Earth's surface would release enough heat energy to boil the oceans dry several times. This is comparable to the statement, your oven has enough energy to set your curtains on fire. They are not on fire, so you don't have an oven. For comparison, the Tsar Bomba released more energy than all weapons and bombs in all wars combined, yet nobody got killed. So two things are important. It's not only the amount of energy that is involved that matters, but also the heat transport. In other words, where is the heat? So heat transport then. How do we get heat from here to there? Basically, there are only three ways to do that: heat flow, conduction, and thermal radiation. If none of these is available, the heat stays where it is. Flow is like this. You have a liquid or a gas that is hot and the material moves. So this is flow and this is no flow. Conduction. Conduction is heat transport by material that is touching each other. So consider we have a hot material touching a cold material in a closed environment and the material doesn't move. After a while, all this material will have a medium temperature. So this is a good conductor and this is a bad conductor. Radiation. Radiation is heat transport by emitting light. If it's very hot, it can be red, yellow or even white. But usually we don't see it because the majority is infrared light. So this is a good radiator and this is a bad radiator. So technically it's possible to trap heat, like heat, inside the earth. Let's take a random example. Assume we have a large piece of rock and suddenly parts of this rock gets molten for some reason. It expands a little, and now let's add water to it. And let's assume the rock contains enough heat to boil all this water away. So the water then starts to boil at some point, and the lava is starting to cool down. The lava sinks slowly, causing some places where hot rock goes upward. And after a while a solid layer forms on top of this molten rock, and then eventually we would have a situation where a solid layer isolates the hot molten rock from the water. So we'd end up with trapped heat and still a lot of water on top. So for all the oceans to evaporate, all heat must end up in the ocean, which does not happen. You see, it's possible to touch freshly solidified lava with your shoes shortly without them catching fire. For your own safety, I highly recommend not to do this, but it is possible. So let's take a look at what would happen if continents shift quickly, exposing hot mantle material. Say the left is South America, the middle part is lava, but this is what is going to be the Atlantic Ocean, and the right is Africa. The lava is lighter than the solid rock, so it expands. Not only does this boil the ocean away there, but it also pushes the ocean away there because of the expansion. The result is that it would start to rain like crazy in colder areas, and that is on the continents. So we would have a situation where the ocean is flooding the continents and the lava has a lot of freedom to expose its heat to the sky and the universe. At the edge of the continents, the water touches the hot lava, enhancing the solidification process there. Because it solidifies, it shrinks and becomes denser than the continents, so it leaves more room for the water there. The molten lava is being squeezed out horizontally and wants to flow on top of the solidified lava. But there's water there, so it also starts to solidify. So the water is slowly pushing the molten lava towards the middle, and eventually 2 layers of solidified lava lean on each other, and this causes a closing seam, a closing midpoint, which we identify today as a mid-oceanic ridge. When it comes to thermal radiation, we can actually calculate how long this would take. For that we need to use the Stefan-Boltzmann law. The result of this formula is energy per time. You get it by multiplying some constant value with the emissivity, the area and the temperature. But the temperature is in the 4th power in this formula, resulting in a tremendous nonlinear process. So the answer is in watts or joules per second, and Stefan's constant is a very small number. The emissivity is a property of the material. We're going to calculate this for basalt, which is what the oceanic floor is made of. The area is in square meters and the temperature is in kelvins. Let's give an example first. If we would have 1 cubic meter of basalt being exposed for only 1 square meter, how long would it take to solidify? And like I said, it strongly depends on the temperature. If it would cool down from 2000 Kelvin to 1900 Kelvin, it would take 399 seconds, which is about 7 minutes. From 1000 to 900 Kelvin, it takes about 2 hours. From 300 to 200 Kelvins, it takes about 20 days. And from 100 to 0 takes forever. It will never reach 0. So this is very strongly nonlinear. Now assume we have 2 blocks of rock. They are made of the same material, they are equally thick, and they are only exposed at the top. But one of these blocks is a lot larger than the other. Which would cool down faster? If we use both the formula for heat capacity and the Stefan-Boltzmann law, we see that the area plays a role in both. More area means more heat capacity in a linear way, but more area means more thermal radiation also in a linear way. This means that in the end, for the cooling down time, area isn't relevant, it's the thickness that matters. So we can make the formulas a little bit simpler. And now we can calculate the thermal radiation for a scenario. What if the entire oceanic crust was molten at the same time? How long would it take to solidify? We use these variables. The thickness of the oceanic crust is about 7 kilometers on average, and we use temperatures that are normal for molten lava, which is a starting temperature of 1600 degrees Celsius and a solidification temperature of 1000 degrees Celsius. For this calculation, it is better to integrate the Stefan-Boltzmann law to get accurate results. Since the temperature is so high, the energy emission is huge. Remember, the temperature is in the 4th power. It takes 1 year and 150 days to solidify, so not billions of years, not millions of years, not even thousands of years, only 1.5 years, because the solidifying process itself also releases energy. This is called latent heat fusion. But also this takes only 2.3 years. So if we would melt the entire oceanic crust at once, it takes only 3.7 years to solidify using thermal radiation alone. Water enhances this solidification process, so we are actually very much in the right order of magnitude for the Genesis flood. If you see my other presentation about the solar system, you see that the evolutionary timescale for things like the moon are very far off. When a crust is solidified, it's still quite hot, about 1000 degrees Celsius. Then conduction takes over for the cooling down process. We can also calculate this. We have a formula that says that heat conduction per time is the thermal conductivity times the area times the temperature difference on both sides of the material divided by the thickness of the layer. To do this properly, we must divide the materials up in smaller layers, because each of these layers have their own temperature, and thus they have their own amount of heat energy and their own conduction speed. All these layers give their energy to their neighbors, and only the top layers releases that energy to cool the whole lot down. So we start with a lot of layers that are 1000 degrees Celsius each, except for the top layer, which is at room temperature. Remember, there's water on top, which consumes a lot of heat. The layers are 50 meters thick each, and we're using a time interval of about 100 days to calculate the conductivity step by step. And we represent the temperature with colors. Red is 1000 degrees Celsius, yellow is 500 and green is 20. Here we display a layer of 7 kilometers thick. This is what it looks like after 90 years, 1000 years, 2000 years, 3000 years, 4000 years, and let's stop at 4500 years. If we are looking at the Genesis flood, it could be that this is close to the time that has passed since. There are uncertainties at when the flood year was, which is a subject for another discussion, but let's just see what the result is after 4500 years. In this scenario, all would have cooled down and we would find the maximum of 590 degrees Celsius at 4700 meters depth.
Remember, we still have a lot of volcanic areas, which are in the basaltic oceanic crust, so conductivity is happening there. Since these are still hot today and only a few kilometers depth, it means these volcanic areas could not be millions of years old. This calculation shows that it can only stay hot for thousands of years. Now when it comes to heat, there are some pretty weird phenomena that come into play. One is a thermocline. You may wonder how fish could survive such a scenario. Let's say we have regions with hot water and regions with cold water. Then there are also places where the hot water flows on top of the cold water. The hot water kills the fishes. Yes, we find a lot of dead fish in the geologic layers. And the fishes in the cold water can survive. The hot water is less dense than the cold water. This causes that hot and cold water don't mix very well. This causes a separation between hot and cold water layers, and this separation is called a thermocline. Important for fishes, but you don't need that information for the rest of this presentation. Now the next issue is power law creep. Power law creep is a process that causes rock to become viscous without increase in temperature. How do you do that? Well, let's assume we have several layers of rock, we put pressure on it, and we are going to push the top layer sideways. That is called shear stress. Then the middle layer will start to deform. In other words, it changes shape. Now if you put a gigantic shear stress on the top layer, the layer below dramatically changes shape. This process is very strongly non-linear and has to do with molecular structures breaking up and crystalline surfaces sliding on top of each other. It's very complex, but it has been tested in the laboratory. You can compare this with toothpaste. Toothpaste is solid until you put pressure on it, then it changes shape, but it will become solid again as soon as the pressure stops. This process reduces the viscosity of the rock up to 14 orders of magnitude, and thus it's very strongly non-linear. In very extreme conditions, solid rock can flow like water, without increase in temperature. The last weird phenomenon I'm going to show you is the crossover depth. We are used to magma rising up because molten material has a lower density than the same material in solid state. But it appears that molten rock is better compressible than solid rock. So if you put a lot of pressure on lava, it will eventually become more dense than the solid rock. So magma that is very deep inside the earth sinks. The point where this switches from rising to sinking is called the crossover depth. Depending on the rock type, the point where this happens is between 200 and 400 kilometers. This phenomenon has also been confirmed by multiple laboratory experiments. And very importantly, it shows that magma cannot come from deeper than 400 kilometers. The crossover depth is about here. What I think that happened is that large impact plus the crossover depth plus power law creep is catastrophic plate tectonics.